Greetings, my name is Nurul Qistina and I'll be presenting for the introduction part as well as the application in the medical field. So, a differential equation is an equation that relates one or more functions and their derivatives. In applications, the functions generally represent physical quantities, the derivatives represent their rates of change, and the differential equation defines a relationship between the two. The existence of differential equation began with the invention of calculus by Isaac Newton, which are dy over dx equals to fx, dy over dx equals to fxy. Differential equations are described by their order, determined by the term with the highest derivatives. An equation containing only first derivatives is a first-order differential equation. An equation containing the second-order derivative is a second-order differential equation, and so on. Homogeneous first-order linear partial differential equation. Curly du over curly dt plus t curly du over curly dx equals to 0. Homogeneous second-order partial differential equation of elliptic the Laplace equation. Curly d square u over curly dx square plus curly d square u over curly dy square equals to 0. And the last.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Alya Irdina binti Zahmat Syari and my metric numbers is 200717. So I am from group 2. Today, I am going to explain about the application of differential equation. So my contribution in this topic, in this assignment is the application in chemistry field. So the first application in the chemistry field is chemical reaction kinetics. So these simple reactions like the transformation of A to B can be described by the differential equation, which is this equation. So as we can see that concentration Ca is exponent 1. So we can describe this as the first order reaction in chemical kinetics. From this equation, we can solve this equation by using the integration when the boundary conditions such that CAT varies between by boundary condition such that CA varies between CAT and AO, and also when the time is run between T and 0. So by following a separation of variable, the integrations will result in this equation, and this equation we will simplify it and become this equation. Next, I am going to explain about the application of differential equation in radioactive decay. So the activity A of sample containing this isotope is defined as the number of atoms disintegrating per time unit, which is the rate of decay. So from here we can see that the differential expression of activity A of isotope is this expression, which is A equal to negative dN over dt. So we can see that the first order differential equation is this negative dN over dt equal to lambda n. From here we can see that follows by ordinary linear homogeneous first order differential equation, which is this equation, and separation of variables of this equation will become like this: dn over n equals to negative lambda dt. So by solve this equation using the limits boundary condition, we can see that the limit we use is initial number of radioactive atoms, NO, and F, final number of radioactive atoms when the time runs from the T to T equals to 0. So from this we can get the result of the integration is this, and we will simplify it to the final equation, which is NF equal to NO E negative lambda T. So from here we can see that equation, the final equation that we get, is describe the exponential decreases of n as a function of t, which is this. So next we will see that differential equation also can be used in the to find the isotope. Isotope gives the time in which half of the initial number of radioactive has been decayed. So like this. If an isotope decays on two different pathways, the overall decay constant is the sum of the two individual decay constants. Like this, two different pathways, and we can get the overall decay by using differential equation. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Sharifah Nurin Zahirah binti Said Zainal Abidin. My metric number is 200501, and today I am going to present on the application of differential equation in molecular biology. So the first one is a study was made by Ita and Ital by utilizing an ODE model to acknowledge how chemotherapy drugs affect the breast cancer cells when it is applied, and to propose a new time-dependent strategy. Signal transmission through protein phosphorylation was represented by ODEs that assumes first and second order mass action kinetics. For example, this is the equation that is involved with protein A. Second one is a research was made by Gupta et al. By using a special type of linear ODE, which is called as Markov model, to study how phenotypes of cancer cells transition naturally under therapeutic stress. The model predicted that at low rate, cancer non-stem-like cells can transition into stem-like cells, which counter the stem-like cells in classical unidirectional view. So the major contribution of Gupta et al. Is a systematic procedure in characterizing how treatments have influenced phenotype transitions in the populations of cancer cells by using data that is collected at 2 time points. And the third one is Goldman et al. Utilized an ODE model to observe the response of phenotype transitions to anti-cancer drugs. He constructed a linear time invariant ODE to theoretically test drug-induced phenotypic plasticity against clonal selection. The model described the changes of the quantity of cells in each phenotype over time using parameters such as net reproductive rates and phenotype switching rates. The model also predicted that chemotherapy tolerant cells can be raised from non-cancer stem-like cells, which was later proven in experiments. And the last one is another study focuses on implementing different types of ordinary differential equation ODE models of tumor growth to make predictions about the efficacy of cancer treatments. The linear ODE equation that is used in this experiment is this equation, and the linear model assumes the initial exponential growth that changes to growth that is constant over time. So that's all from me. Thank you.
My name is Nur Sabrina. My metric number is 203138. I will explain about application of differential equation in logistic equation in economics field. So this is the example of situation. The situation is, let n in terms of t be the number of individuals in population at time t, and let b and d be the average per capita birth rate and death rate respectively, and delta t the number of births in the population in a short time delta t. In the short time delta t, the number of births in the population is b delta tn, and the number of dates is d delta tn. And the equation for n at time t plus delta t is this, and we arrange this equation into this, and we substitute delta t equals to 0 and r equals to b minus t, and we have this equation. And then this is equation of the population size grow exponentially under a Malthusian growth model, which is n0 is the initial population size. When the population growth is constrained by limited resources, the heuristic modification to the Malthusian growth model result in the Verhulst equation is this, which is K is the carrying capacity in the capacity of the environment, and dimensionless using T equals to RT and X equals to N divided by N per K leads to the logistic equation, which is this. And we assume the initial condition x0 equals to x0 greater than 0. We integrate this equation, and the integral of left-hand side can be done using the method of partial fractions, which is this is a partial fraction. And then the cover-up method yields A equals to B equals to 1. Therefore, we got this. And the next step is first exponentiate both sides, then isolate x. After that, we observe that for x0 greater than 0, we have limit t approaches to infinity, x in terms of t equals to 1 corresponding to this. Therefore, the population grows in size until it reaches the carrying capacity of its environment. Next one is compound interest. This is the calculation is quite same, which is we have this value of investment at time t plus delta t, and then which is k delta t is amount of money deposit, and we have the value, which is r equals to 6% per year, delta t is equals to month, and equals to years. And then we substitute, we derive the equation, and then we substitute delta t equals to 0, and the differential equation is this, and we integrate it from t0 to a final time t, and then we got the final is this equation, where the first term of the right hand side of this equation comes from the initial invest capital, and the second terms come from deposit of withdraw. Evidently, compounding result in the exponential growth of investment. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Shahirah Atifah with my matrix number 202468. Okay, for the assignment 1, the mathematics project 2, my contribution in this assignment 1 project is I'm doing the application of engineering technology. Okay, for engineering technology, is the rate of change of QT, or we call the rate of change of QT, or we call is the amount of substance dissolved in the liquid in the tank of any time any time equal to the rate of which the amount of substance dissolved in the liquid in a tank enter the tank, plus the rate of which the amount of the substance dissolved in the liquid exit the tank. Or we can use another equation that is VO plus Q, the amount of dissolved substance, the amount of substance dissolved in the liquid into minus the amount of dissolved substance dissolved in the liquid out times the differential of time plus the amount of dissolved the amount of substance dissolved in the liquid enter the tank, and here there's an example that I give for the question for the engineering technology application that involve the linear order differential equation. That's my contribution in the